Welcome everyone. I'm Norman Wahlberger, and this is the second of our lectures in this course on Elementary Mathematics Explained, which is going to attempt to clarify what's going on with the mathematics that students learn in years kindergarten through year 6. Especially important for teachers, for parents of young students, and for anybody wanting to strengthen their mathematics right from the ground up. Today's lecture is concerned with arithmetic with rectangles. So we're combining, in a very natural way, the two main subjects in mathematics, arithmetic and geometry. Now, it's well known that in the years K to 6, most of the mathematics that students tackle concerns arithmetic. And it's probably not too much of an exaggeration to say that if you master that arithmetic, then success in mathematics is almost assured, because it forms the foundation for almost all subsequent work in the subject. Well, what is arithmetic? Broadly, we can say that it's the study of numbers and operations on them. So there are two key operational words here, numbers and operations. What do we mean by numbers? Well, there are different kinds of number systems that we learn to do arithmetic with. And they kind of have an order of difficulty or complexity. The simplest are the natural numbers or the counting numbers. 1, 2, 3, 4, 5, 6, and so on. Those are the simplest kinds of numbers, and those are the first kinds of numbers that we learn to do arithmetic with. A little bit later on, we move to integers, where we also add 0, which is very important, and some negative numbers, -1, -2, -3, and so on. And then a little bit later, we talk about fractions like 1/2 or 13/5, and then decimals like 12.41, and so on. So each of these is a kind of a little self-contained system, and each of them supports various operations. So the main operations in elementary mathematics are addition and sort of the inverse operation of subtraction, multiplication, and its inverse operation of division. There's a secondary operation which also becomes important later on of exponentiation. But it's safe to say that these first four are the most fundamental, and it's probably safe to say that addition and multiplication are the two really crucial operations. In this video, we're going to stick with the simplest number framework, that of the natural numbers, and we're going to discuss the simplest and most important operations, addition and multiplication. But we're going to do so in a very geometrical way. We're going to go back in time almost to a almost prehistoric point of view, or if you like, we're going to descend right to the kindergarten level. So we're going to think about arithmetic with natural numbers and these two operations in terms of rectangles and very simple operations geometrically defined. So let's start off with the natural numbers, sometimes called counting numbers, because they're the numbers that we use to count with. All right, here's the first few. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and so on. Sometimes people like to include 0 as a natural number, and it's a matter of convention whether we agree that 0 is a natural number or not. But historically, 0 has been quite separate from these numbers. And I think it's natural when you're learning the subject to think of the natural numbers as starting from 1. That's what we're going to do. Now, this presentation of the natural numbers, of course, is very familiar to you, even if you hate mathematics and did very poorly at it in school. You will all be familiar with this. This is a particular way of representing natural numbers that's actually called the Hindu Arabic number system. It was developed in India around 800 AD. It took quite a long time to develop, and it was subsequently honed and perfected by Arab mathematicians. And I say that very broadly, so Arab-speaking mathematicians, including Persians and other people. Now I put a triple star beside this. In my opinion, the development of the Hindu-Arabic number system is not just one of the key developments in modern science, it is the paramount development in the history of science. There is no other development that compares in importance with the development of this number system. It is so important in forming a basis for the modern world in which we live in. This is a story that's seldom told, I think, adequately to people starting out in this subject. And it will be a story that we will have a lot of contact with in this course, because the Hindu-Arabic number system features prominently in the education of young people and the foundations of mathematics. There were lots of other number systems that predated this one. So the Romans had a system, the ancient Greeks did, the Babylonians did, the Egyptians did, the Chinese did, the Mayans did. Almost every major culture had a number system. They were all far inferior to this system. Far inferior, all of them. And it's a very interesting thing to think about, that when we are teaching our young children arithmetic in this system, we are actually presenting them with a very powerful and finely tuned technological system. It's a little bit like getting a young person to learn how to drive in a Ferrari. That's sort of essentially what we're doing. And there's something perverse about that. It's great to drive a Ferrari, no doubt. I've never done it. But probably one should not learn to drive in a Ferrari because it's too powerful. It has too many bells and whistles, just too much under the bonnet. Probably better to start learning to drive with a much simpler, more basic kind of vehicle. That's a point of view that we're going to adopt. So why is this system so great? Well, because the four main operations in mathematics within this system are much easier than they are in any other system. So here's an example of an addition, a subtraction, a multiplication, and a division, all done in the Hindu-Arabic number system. And these four things are all fundamental operations that students eventually learn and that you will eventually learn too. Addition of numbers, subtraction, multiplication, division. So one of our aims is to understand these completely. But not just understand them at the algorithmic level. Not just a question of understanding what you do in order to get an answer. But more importantly, try to understand why they work. Why they work gives us a much bigger view of the mathematics. Makes everything much simpler to understand. But we're not going to start with the Hindu-Arabic number system because it's too sophisticated. It's too powerful. We're going to go back in time to a much earlier time. We're going to go back in simplicity to much simpler kind of notation. And we're going to start our arithmetic in a very basic elementary way, which is a good way to start. So we're going to start our study of arithmetic by going back to a much earlier, more primitive, more natural presentation of numbers. Long before major cultures developed, tens of thousands of years ago, perhaps even hundreds of thousands of years ago, our ancestors would have lived in small tribal groups. And they would have had need to do some basic arithmetic, usually just some simple counting now and then. To count the number of animals at a water hole, to count the number of kids that were taken care of, to count the number of sheep in a flock, to count the number of days till the next full moon. These kind of counting problems involve some appreciation of simple, relatively small numbers. And we don't know when numbers first officially made their appearance. Probably they were discovered many times during the course of our history. Of course, these are lost to us. We don't know who these people were who started working with numbers. But we can be reasonably sure that numbers started in a very simple representational kind of way. By, for example, strokes on a piece of bark, or maybe a certain number of pebbles held in the hand. So, to these very early mathematicians, counting would have been done in some very primitive way like this, where each number was represented by a bunch of, say, strokes on a piece of bark. Each number followed by the next one, which simply has one more stroke on it. So to go from one number to the other, we just add a stroke. Or if we're working with, say, pebbles or shells, just add a pebble or a shell to go from each number to the next one. So whether we work with strokes, whether we work with little circles representing shells, or whether we work with little boxes, it's sort of figuratively pretty well the same thing. But there's something very pleasant about working with boxes, because first of all, it's a little bit easier to visualize than these ones. It's somehow, for us, a little bit easier to see the 5 here rather than the 5 here or the 5 here, I think. And moreover, this kind of representation of numbers fits very nicely with our understanding of the grid plane that we talked about in our last lecture. So, to the question, what is a natural number? We're going to give the following answer. A natural number is a row of cells. Something like this. Or in more fancy language, it's a rectangle, which just consists of a single row. We might call it a row rectangle. So that's what a number is. That's a very primitive and, in fact, natural way of thinking what a number is. What about names for numbers? Well, it took a long while for people to develop names for numbers. And for the first large part of the history of these numbers, there probably weren't very fancy names for them. Let's introduce the name 1 for this one. Okay, that number we'll call 1. Then this number we could call 1, 1. That's kind of natural. This number we could call 1, 1, 1. And this number 1, 1, 1, 1. And so on. That's not very sophisticated, but it doesn't require us to make up new names for things. So I'd like to think of this kind of approach to natural numbers as being very suitable for kindergarten. And it's kind of a kindergarten level of understanding of natural numbers. Natural numbers is a row of cells. We are not assuming our Hindu-Arabic notation. We're not assuming that we have the current names for all these various numbers that I know you and I both know. So instead of calling this 5, which we're tempted to do, let's, for now at least, agree that this is the number 1, 1, 1, 1, 1. Okay, so can we do arithmetic with these very simple kinds of numbers? Well, yes, we can. And doing arithmetic with them really clarifies what arithmetic is about. It makes it simpler to understand arithmetic. That's the big advantage of it. And then when we finally do end up getting to the Hindu-Arabic number system, we'll fully be able to appreciate the power that it contains. So what are numbers used for? Well, their primary purpose is for counting and measurement. For counting and measurement. That's what numbers are used for. So let's illustrate counting with some examples. Suppose we want to count how many things there are in this collection. Okay, you can see a number of hearts, you can see some blue diamonds, and then you can see some sort of circles with the crosses inside them. So for us, of course, it's very easy. We would just go, well, there are 4 hearts, and there are 6 diamonds, and there are 3 circles. But let's suppose that we have our kindergarten understanding of numbers. How would we count various things with this very simple-minded approach? Well, the idea of counting, which itself is a very important but simple idea, is that to each object we're going to associate a cell or a box. Remember, one of these little cells, we're calling that the number 1. That's the only number that actually has a real name by itself. So every object gets associated a cell. Or if we were working with strokes on a piece of bark, each object would get a stroke. Or each object would be assigned a shell or a pebble or whatever system we're working with. But we've agreed to work with boxes for now. All right, so let's count some of the things in this collection. Let's count the number of hearts. How do we do that? Well, we go through the hearts one by one, and for each one of the hearts we put down a cell. So let's say for that one we make a cell. For this one we make a cell, this one we make a cell, and this one we make a cell. We check that we've gone through each of the hearts exactly once. We haven't gone over any one twice, and we haven't left out any hearts. So there's a cell for every heart. And then we put the cells together because we want to have a row. We get this rectangle. So this is a number that represents the hearts in the box. Well, how about diamonds? Well, it's the same kind of idea. To every diamond, we're going to associate a cell. And then we're going to put all those cells together in a row. So this diamond, that cell. This diamond, that cell. This diamond, that cell. This one, this cell. This one, this cell. This one, this cell. Each diamond gets a cell, and so the total number of cells is represented by that number. That's a number. Number of circles. That circle gets that cell, that circle gets that cell, that circle gets that cell. There are 1, 1, 1 circles. So if we had to use words, well, we don't have a lot of words for numbers. There's only the number 1. So if someone asked us, well, how many hearts are there? And we had to say something as opposed to showing them, we would say there's 1, 1, 1, 1 hearts. And how many diamonds are there? There's 1, 1, 1, 1, 1, 1 diamonds. And how many circles are there? There are 1, 1, 1 circles. Suppose now we are interested in the total number of objects in the box. Well, here's an interesting idea now, that one way of doing that would be to start again and to list a cell for every object in the box, having to go through all the objects again. But a smarter thing would be to say, well, we've already counted the hearts, we've already counted the diamonds, we've already counted the circles, so why don't we just put all those boxes together? Doesn't that make sense? So in fact, we don't actually even have to go back to the diagram. We know hearts, we know the number of hearts, we know the number of diamonds, we know the number of circles, so we're going to just put those together to find the total number. So we just take these 3 rectangles, shove them together to make a single row rectangle. That one right there. And I put these little arrows here just to illustrate where the original pieces kind of merge together. So that's that piece there, that's that one there, and that's that one there. So what's the answer to the total number of objects in the little box? Well, the only answer we can give, if we're going to say an answer, would be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. That's how many objects there are in the box. So we're doing kindergarten arithmetic, but it's still a little bit interesting. So besides counting collections like number of animals in a certain place, or number of children, or number of people in an opposing tribe, our early ancestors would also have been interested in the motion of the heavens and basic calendar keeping. Especially once agriculture became established, then keeping a regular calendar, keeping track of the seasons, became more and more important. And for that, let's talk a little bit about the motion of the Earth around the Sun and the motion of the Moon around the Earth. So in this picture here, we imagine the Sun somewhere over there. And this blue sphere here represents the Earth, which is going around the Sun in a roughly circular orbit. And that orbit takes 1 year to complete. So after a year, the Earth is back to where it started. Now, as the Earth is traveling around, it's also spinning on its axis. Spinning around its axis, and it keeps on spinning as it goes around, and it spins once around every day. That's the source of our day, the spinning around of the Earth. But the other player in this little drama is the Moon. The Moon is going around the Earth. And it's roughly in the same plane as sort of the plane of the Sun and the Earth. So we can think of this as sort of a top view. We're looking down on the Earth, we're looking down on the Moon. The Earth is traveling in the plane of the board along this circular arc, and the Moon at the same time is going around the Earth. So as the Earth moves, well, the Moon is still making this circular orbit around the Earth. And how long does it take for the Moon to go around? It takes roughly a month. And that's the source of the month as a unit of time. Well, if we look at it a little bit more carefully, though, there are in fact two possible interpretations of what a month is. So, as the Earth goes from this position to this position, let's say that's exactly the amount of time required for the Moon to go all the way around and return to the same relative position as it did before. So this direction from the Earth to the Moon is parallel to this direction from the Earth to the Moon. So if you just looked at the Earth and the Moon, you would say that the Moon is back to where it started. However, with respect to the Sun, the Earth has moved. So when the Moon is behind the Earth like this, that's like a full moon position. That means the Sun is shining completely on the face of the Moon, and the entire face of the Moon is visible to the Earth. That's when you see a full moon. When the Moon is sort of on this side of the Earth, then you don't see any part of the lighted part of the Moon, and that's a new moon. It's dark. When the Moon is over here or over here, then half of the lit up side of the Moon is visible, and you kind of see a half moon. All right, so this is the position for the full moon, and so by the time it's gone around here, you would say, well, this might also be full moon, but it's not quite a full moon, because the Earth has moved from here to here. So if you just look at the rays from the Sun, the Moon is not quite yet behind the Earth with regard to the Sun. It will be a little bit longer before the Moon actually moves behind the Earth in its relation to the Sun. So that means that the period that it takes for the Moon to actually make a complete revolution, which is called a sidereal month, is somewhat less than it takes from one full moon to another full moon, which is called a lunar month. Okay, so astronomers know all about that kind of stuff and have been studying that for thousands of years. So it turns out that the time for the Moon to make one full revolution around the Earth is 27 or 28 days. But the time from one full moon to the next full moon is slightly more. It's roughly 30 days, or maybe a little bit less. So a natural thing that a mathematically inclined watcher of the skies would do is to count the number of days from one full moon to another. And how would you make such a count before we actually had any symbols for numbers, before we actually had names for numbers? Well, you would make a mark on a piece of paper, one for every day. And our marks here are little squares. So this observer would make a square for every day that passed from one full moon to another. And at the end of that experiment, he would say, this is the number of days from one full moon to another. And if you had to say what that number was, I guess the only thing he could say is, well, it's 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1. And it would naturally probably occur to him that maybe he should think of a more efficient way of saying that. Okay. Obviously, for large numbers, this notation, this way of representing them, is going to get awkward. So as we become a little bit more sophisticated in the kinds of things we're counting, we are going to be wanting to introduce more efficient notation and more efficient terminology. But let's stick for now with this kindergarten approach. So the idea of counting a collection naturally leads to the idea of the size of a collection. So for example, suppose that I have a coin collection. We might go back to the ancient Greeks, who first started printing coins 500 or 600 years before Christ. So I've collected a bunch of coins. Maybe they're different sizes, different denominations, and you also have a coin collection of different sizes, different denominations. Let's give a name to my collection. Let's call it X. Let's give a name to your collection. Let's call it Y. And suppose we are interested in whose collection has more coins in it. Well, your collection and my collection might be in different places. I might have my collection hidden in my house, and you have your collection hidden in your house, or maybe we live far apart in different villages. So one way of deciding that is to count how many are in my collection and to count how many are in your collection. So how do we do this counting? Well, the size of X, and we're going to use this hopefully familiar terminology, 2 bars around the X to denote the size of this collection. To find out what that is, what we're going to do is we're going to introduce a cell for every coin. So I'm going to go through my collection, one coin at a time, and write down a cell for each of my coins. And I'm going to have to do this sort of consistently so that I don't miss a coin, and so I don't duplicate any coin. So just make sure that I'm doing that right. So this coin here, I'm going to make that cell. This coin here, that cell. This one here, that one. This one here, that. This one here, that. This one here, that one. This one here, this one. This one gets that. This one there. This one there. And this one there. So I've written down one cell for every one of my coins. And now I put all those cells together to make a rectangle. And that's now a number. We agree that's a number. So that number is the size of X. And we could record that on a piece of bark. We could draw that on a piece of bark and say, that's the number that represents the size of my coin collection. And now we go over to your village, and we're going to count how many coins you have. And we're going to do the same thing. So systematically, we're going to write down a cell for every one of your coins. So check that I'm doing this right. So that one gets this one, here, this one, here, this one there, 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 this one, this one, this one there, this one there, and this one there. Okay, we put those all together to form a rectangle. That's the number of coins in your collection. That's the size of Y. Now we don't have to worry about the coin collections anymore. We can now just compare the numbers. So I have the number of my coins on a piece of bark. You have the number of coins in your collection on a piece of bark. We can compare our two numbers. How do we do that? Well, an informal way would be just to sort of look at them and say, well, it looks a little bit like yours is a bit longer, but I'm not sure. Let's do that more systematically. We could do that by just going through them one by one. We match, these are matched up, these are matched up, these, I'm matching them up one at a time, one for one, to see whose number is bigger. And yours is bigger by 1. We can say that the size of Y is bigger than the size of X. And we're going to introduce some notation for that sentence. We're going to introduce this notation. There's the size of X, there's the size of Y, and this symbol is going to represent the fact that the size of X is less than the size of Y. Or that the size of Y is bigger than the size of X. So the pointy part, the sort of small part of the symbol, points to the smaller number. The wide part of the symbol points to the bigger number. And we read this left to right. We say the size of x is less than the size of y. That's reflected in these two numbers. So numbers are important not just for counting, but also to measure the relative sizes of different collections. That less than sign that we introduced on the last slide is one of three possible relations between two numbers. So there are three, or from a kindergarten point of view, 1, 1, 1, possible relations between any two, i.e. 1, 1 numbers. What are those relations? That's one of them. That's equality. This is less than. This is greater than. Okay, what do they mean? Well, this one is equality. It means that the numbers are the same. There's the same number of cells in this number as in this number. This example illustrates that the size of the rectangles that we're using is not really important. Okay? This number and this number are in fact the same, because the cells here and the cells here can be matched up. This matches with that, this matches with that, this matches with that. So you don't get a bigger number by writing your number bigger. You only get a number that's bigger by adding more cells. Okay, how about these two? This is saying that this number is less than this number. Well, it kind of looks like it geometrically. How do we check that? We check that by comparing them one by one. We'll match these, 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 these. And there are now 1, 1, 1 more here than here. So this one is a bigger number than this one. This relation is greater than relation. This number on the left now is bigger than this number. You can see that kind of obviously, but you can also check it by matching them up one by one and seeing that there's more left over on this side. So our terminology is A equals B, that we say A equals B. This symbol here is A is less than B. That's how we read it. We read from left to right, so A is less than B. And this symbol here is A is greater than B. These three relations, equals, less than, greater than. And with this relatively primitive idea of number, these are natural geometrical relations. We can see them almost directly physically. So now we're ready to introduce the two most important arithmetical operations, which are addition and multiplication. Both of them are relatively simple, perhaps surprisingly simple, in this simple kindergarten geometrical framework. First of all, addition. To add two numbers, we just join the row rectangles. So for example, here's a number, here's a number. If we add them, which is represented by this symbol, the cross, this number plus this number, what we get is just the new number formed by combining those two numbers physically, just moving them up so that they're touching. So there's the first one. I'm sort of indicating where the original line of separation has been put together to join them. There's the first one on the left. There's the second one on the right. We've joined them up. So how would we read this equation? Well, we would read it in the following way. The number 1, 1, 1, 1 plus the number 1, 1, 1 equals the number 1, 1, 1, 1, 1, 1, 1. In terms of counting, this corresponds to forming the sum of two collections of objects, forming a sum by the simplest possible way of just combining them. So here's one collection. Think of it as a jar holding a bunch of things. Here's another collection, another jar holding a couple of things. The number in this jar is 1, 1, 1, 1. 1, 1, 1, 1. The number in this jar is 1, 1, 1. If we combine the contents of the two jars, just dump them all into another jar, then you're going to get all these objects. So 2 circles plus 1, 2 black rectangles plus another one, and the green rectangle. So the two collections have been combined to get this one, and then the total number is 1, 1, 1, 1, 1, 1, 1, as illustrated there. Addition is very simple in this format. It's dramatically simpler than it is in the Hindu-Arabic number system. Right? To add 2 numbers, you just put them together. That's it, you're finished. We can also add more than 2 numbers. So if we want to add 1, 1, 1 plus 1 plus 1, 1, 1, 1, 1, we just take those 3 rectangles, shove them together to get the number 1, 1, 1, 1, 1, 1, 1, 1, 1. Very simple arithmetic. The other important operation is multiplication of 2 numbers. So now I'm going to define what multiplication of 2 numbers is. So this is a definition. So to multiply 2 numbers, we form the rectangle whose dimensions are these numbers and count its cells. So here is the number 1, 1. Here's the number 1, 1, 1. So 1, 1 times 1, 1, 1. What is it? Well, we have to make a rectangle. And the number of rows in this rectangle has to be 1, 1. 1, 1. And the number of columns has to be 1, 1, 1. 1, 1, 1. In our modern language, just to interject for a second, we're multiplying 2 times 3, so we're creating a 2 by 3 rectangle. The number of rows is that first number, the number of columns is that second number. And then we have to count how many cells this thing has. Well, it has 1, 1, 1, 1, 1, 1. And I've put them down here. 1, 1, 1, 1, 1, 1. And that counting is really just a rearrangement of the cells. What we're really doing is just separating the rows and separating them and putting them together to form one long row. Because we've agreed that a number is a row rectangle. We've got to get a row rectangle as the end result. Here's another example. Let's multiply 3 times 5, or in our language, 1, 1, 1 times 1, 1, 1, 1, 1. So we make a rectangle which has 3 rows and 5 columns, a 3 by 5 rectangle. Or in our kindergarten language, which has 1, 1, 1 rows and has 1, 1, 1, 1, 1 columns. So the rows are matched up with this number, the columns are matched up with this number. And now we have to count the number of cells in this thing. And that's easiest done by just thinking of the 3 rows and separating it into 3 rows. There's the first row, there's the second row, there's the third row. And then just putting them together. And we get the 3 pieces there. So the answer is 15, but in our language, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. That's how we do multiplication in this kindergarten framework. This example is a little bit more sophisticated. We're going to try to show this equation. Let's have a look at it. So it's this thing here equals this thing here. So there's kind of a left-hand side and a right-hand side. On the left-hand side we have, well, there's something in brackets. What's inside in brackets is 1, 1, 1 times 1, 1, 1. The brackets are a convention for do this first. So when we see something in brackets, we are going to agree that we're going to do that first. So when we do that, we're going to get some number. And then we're going to take that number and we're going to add 1 to it. And on the right-hand side, we just have 1, 1 times 1, 1, 1, 1, 1. Now to skip forward a few hundred or thousands years, just briefly, what is this really saying in the Hindu-Arabic number system? It's saying that 3 times 3 plus 1 equals 2 times 5. Okay, we all know 3 times 3 is 9. If you add 1, that's 10. And 10 is the same as 2 times 5. So that's a true statement. But we're going to verify that using our kindergarten idea of the operations. So let's do that. So step by step. The first thing, let's compute 111 times 111. How do we do that? We make a rectangle with this number of rows and this number of columns. Then we separate that rectangle out into its various rows and combine them. Or in other words, we're counting the area of this rectangle. And that's 1, 1, 1, 1, 1, 1, 1, 1, 1. The next thing we're supposed to do is we're supposed to take this number and we're supposed to add 1. So now this is the whole left-hand side. This thing plus 1. Well, there's the number that we just got. I'm just copying this again. Let me just make sure I've copied it right. This matches, match, 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 match. So this number really is the same as that number. And now I have to add 1. Well, add 1 just means we're going to slot it on there, and you can check that that's the same with 1 more. Also, on the right-hand side, 1, 1 times 1, 1, 1, 1, 1. We have to make a 2 by 5 rectangle, 1, 1 rows, and 1, 1, 1, 1, 1 columns. Then we separate that into forming a row rectangle, and the answer is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, are these things equal? Is this equal to this? That's what we want to check. How do we check whether two numbers are equal? In this context, there's only one way of doing it. You have to go through them and compare them one at a time. So let's do that. Here, 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 here. We've matched them up one cell at a time. There's none left over when we get to the end on either side. So there's a complete matching up. These numbers are equal. We have proven this equals this. Okay, I claim this is the way kindergarten kids ought to learn addition and multiplication. It's not so important, in my opinion, that the kids learn the Hindu-Arabic number system. That they learn the numbers 1, 2, 3, the symbols that we use for them. Because the problem with that is they start thinking of the numbers as being the symbols. The symbol 4 that we write is really only a representational device for that number. That's the more fundamental way of thinking about the number. The symbol 4 that we write down is just a way of sort of efficiently encoding that. It's a lot better if students learn the essential aspect of the objects that they're working with. So the numbers are row rectangles. And then the operations of addition and multiplication are easy for them to check. They can easily make, or with a little bit of work, and it's kind of fun work, to check arithmetical statements like this. So now let me give you some practice to see how you do at this kind of kindergarten arithmetic. All right, so our exercises for today are to check the following equations using only kindergarten arithmetic. So no use of Hindu-Arabic numbers, please. No use of your calculator, certainly. Okay? I want you to just follow the definitions of addition and multiplication that we've given completely geometrically to check that 1, 1 times 1, 1, 1, 1 plus 1, 1, 1, 1, 1, 1, 1 equals 1, 1, 1 times 1, 1, 1, 1, 1. That's exercise 2.1. This one says that if you take 1, 1, 1 times 1, 1, 1 and you add 1, 1, 1, 1 times 1, 1, 1, 1. So first you compute this, then you compute that, then you add those two. Then you get the same as 1, 1, 1, 1, 1 times 1, 1, 1, 1, 1. Okay, I might not say all of them. I think you can hopefully read what you have to do. This times this equals this times this. This times this plus this equals this times this plus this. This times this plus 1 equals this times this. Now please don't think, oh, this is too easy, this is too elementary, of course it's completely obvious. It's very good to do things even if they're obvious, because in a month or 2 months or a year from now, Having done this will make sure that that's more solid in your mind. And it will give you an appreciation for the geometrical aspect of natural number arithmetic, which in fact, as I mentioned before, actually goes back to the ancient Greeks, and we'll talk about that a little bit later. So next time, we're going to have a look at number systems that follow from this very primitive kindergarten point of view. You can see that the problem with this approach is it's fine if the numbers are small. But once the numbers start getting very big, it's cumbersome to do arithmetic with them, and it's cumbersome to describe the results of the arithmetic. So all ancient civilizations wrestled with the problem of how to compress this kind of arithmetic. This kind of arithmetic, something like it, would have been present at some level in almost every ancient civilization. And at some point they would have realized, wait, we got to do this more efficiently. And they would have introduced shorthands, shortcuts to compress and to encode numbers more efficiently. We're going to talk a little bit about history next time, about various historical attempts at solving this problem, which of course culminates in our current system, the Hindu-Arabic number system, which is such a triumph of modern thought. Well, not so modern, more than 1,000 years ago. So we are moving towards a real deep appreciation of this number system that underlies the education of modern young people. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.